Thank you for coming to our poster. We'll talk about this study we've done in monitoring metabolite dynamics in patient-derived tumoroids using automated microfluidic Pu.MA system. Monitoring metabolite dynamics in physiologically relevant patient-derived models can provide valuable data for understanding metabolic perturbation during disease progression, drug response, and resistance. In this study, we assayed the glucometabolic changes in response to anti-cancer drugs in triple-negative breast cancer tumoroids. We demonstrate here a novel approach that utilizes an automated 3D assay Pu.MA system. Pu.MA is a microfluidic-based system that is designed to automate assays for 3D cell-based models like organoids, tumoroids. It is a benchtop instrument that uses a microprocessor-controlled pneumatic system to move fluid between wells via pressure differentials. The heart of the system is Flowchips. Each Pu.MA system flowchip contains 8 lanes of reagent wells connected by microfluidic channels. 4 flowchips are placed in a holder that locates all wells in a 384 multi-way plate format, providing for 32 samples per assay. Each test lane designated to one organoid or spheroid sample and consists of sample well connected to the reagent well via microfluidic channels. Flowchip can be filled with any reagents like media, compounds, or stains, depending on the assay configuration. Organoids are loaded into the sample well and located in a protected chamber at the bottom of the well. This allows reagents to be directed in and out of the sample well without disturbing or drying out the sample. The bottom of the flowchip is a thin cyclic olefin copolymer film, which makes it compatible with high-resolution imaging. The diameter of the protected sample chamber is 1.2 millimeters, which allows you to accommodate samples of 800 micron to 1 millimeter in size. The advantage of the system is that you can run 3D assays under physiological conditions, avoiding samples damage or loss. In this study, we use primary cells called TU-BCX4IC, derived from a triple-negative breast cancer patient. The cells were created in Dr. Burrows' lab at Tulane University. Primary tumor is characterized as metaplastic subtype, aggressive and resistant to Taxol therapy. Isolated primary cells were used to create tumoroids by culturing the cells in ultra-low attachment well plate for up to 72 hours. Then created tumoroids were transferred to the flowchip for further automated drug treatment and assay execution, downstream measurement, and imaging. As a first step in our experiments, we incorporated a pretreatment step when we measure tumoroid viability and assess how uniform they are using real-time Glo luminescence assay. Here you can see schematically the principle of the assay. Real-time Glo assay is based on constant presence of viable cells and measures cell viability in real time continually. Assay reagent containing pro-substrate is added to cells. This pre-substrate is then taken up by cells and is converted to a substrate, which then in turn reacts with luciferase substrate present in the reagent mixture and results in luminescence, which is measured by plate reader. The more viable cells you have, the higher luminescence signal will be. Doing this assay is straightforward in 2D culture, but once we move to 3D cell models, factors like sphere size and reagent penetration come into play. In this study, we optimized this assay for use in 3D cell-based models. The assay was done by adding real-time Glo reagent directly to tumoroids in the flowchip and measuring luminescence using GloMax plate reader. In this figure on the left, you can see that assay showed good linearity of the luminescence signal over a range of cell densities. In this figure on the right, we show high signal-to-noise ratio. We also have observed the variability in luminescence signal of 26% between a set of tumoroids, which was quite a good result given the complexity of 3D models. This assay can be used as a data normalization factor at the beginning of the experiment. Here we demonstrate a novel workflow that we have developed to monitor metabolite dynamics in physiologically relevant patient-derived models. In this workflow, we first loaded the flowchip with tumoroids and media containing drugs. After that, flowchip is transferred inside the Pu.MA system. You select the protocol to run from the list and press run. During the automated protocol, the following steps will be done automatically. Media with drug was transferred from an adjacent reagent well of the flowchip to the sample well with tumoroid and incubated for 3 hours. After incubation, the media containing secreted factors and metabolites was transferred back to the reagent well it came from and replaced with fresh media with drug from another well for the next 3-hour treatment. The cycle repeated 5 times and resulted in collection of 5 supernatant samples. The first cycle was done with medium only for baseline secretion assessment, followed by 4-hour treatment cycles for the total treatment duration of 12 hours. This approach allows dynamic monitoring of metabolite secretion over the course of treatment. After the protocol is completed, Flowchips are removed from the instrument, and collected supernatants can be either stored at -20 degrees until further processing or used immediately for the Metabolite-Glo assays. For most tumors, aerobic glycolysis is a major driver of cancer progression, resistance to chemotherapy, and poor patient outcome. Lactate, a product of glycolysis, plays a role in tumor progression and is linked to drug resistance in breast cancer. Therefore, in this experiment, we use Lactate-Glo assay to assess the effect of drug treatment on glycolytic function of tumoroids, and specifically lactate secretion as a product of glycolysis. In this experiment, tumoroids were treated with 3 drugs: romidepsin, an HDAC inhibitor, trametinib, MEK inhibitor, and paclitaxel. Collected supernatants were then used for the Lactate-Glo assay. In this experiment, lactate detection reagent is mixed with the supernatant. After that, the plate is incubated and luminescence signal is measured using plate reader. The luminescence signal is directly proportional to the amount of lactate present in the supernatant. Our data shows that tumoroid treatment of over 9 to 12 hours resulted in a statistically significant increase in lactate secretion for paclitaxel and romidepsin, which indicates drug-induced shift towards glycolysis. Our observations were in line with previously published reports linking the treatment with paclitaxel with increased lactate production, which plays a role in mediating chemoresistance in breast cancer cells. At the end of the treatment, tumoroids were also analyzed for viability using confocal imaging. For that, they were stained with calcine-M, yttrium homodimer, and HOXT. Here you can see maximum projection images of confocal Z-stack. There were marked phenotypic changes observed in the tumoroids after compound treatment, decrease of live cell staining, calcine-M positive cells, and increase in the number of dead cells which are yttrium homodimer positive. These images were then quantified and translated to dose-response curves. The reported IC50 values show different sensitivities to these drugs, and IC50 values for romidepsin and trametinib were approximately 17 or 25 nanomolar, as compared to paclitaxel, which demonstrated IC50 value greater than 1 micromolar, which is much greater than typically reported for breast cancer models. This is consistent with previously published taxane resistance of this 4IC primary tumor. And to conclude, Pu.MA system performs automated complex organoid assay protocols with 3D cell models within the incubator environment. Samples are protected from damage or loss during assay in Pu.MA system. Metabolite dynamic automated workflow in patient-derived tumoroids is an available tool for studying disease progression, drug resistance, identifying new therapies, and advancing personalized medicine. Further work is ongoing to determine relation of metabolism dynamics to compound mechanism of action.